ただの壁紙。
So I'm going to start a presentation about the study the operation of soft switching by parasitic components at 27.12 megahertz class C inverter. So I'll be thankful for your consideration. I'm going to introduce the background and the objective and review some literature and the simulation methodology and how to calculate certain values, and then the simulation with its discussion and the conclusion at the end. So as a background, in the field of DC-AC power conversion, we focus on performance and the efficiency by reducing active and passive components. And increase the power density. So capacitors are widely used, but the passive components in non-ideal capacitor stops instantaneous transfer of stored energy to the load. And the equivalent circuit model of a practical capacitor has ESL, which causes a magnetic buildup and stops the instantaneous transfer. And so we have to consider this and optimize it for higher switching frequencies. The objective is to perform ZVS, 0 volt switching, in a 27.12 megahertz class D resonant DC-AC inverter, and analyze the effect of ESL. And here also we will evaluate for what range and value of ESL we get the desired result for our operation. So for the review in the soft switching, we have the transient for voltage and current, the switching loss, and we can remove it by making it 0 volts, which means we make the increase the current only once the voltage is 0. We can do this. One way to do this, I will be using it later, is to include a phase difference in the current, so that the current gets, the phase gets delayed, and the current increases only when the voltage is 0. So about the half-bridge inverter, we will have a DC wave, which will move into a square wave with switching device S1 and S2. And then we will make it into a sinusoidal wave, ideally with the help of this resonator tank. So in my simulation, I'm going to use I'm going to divide it basically two parts: a resonance circuit, which will include our capacitor, and we will be evaluating for what value of parasitic components and so further, and the switching circuit, which will be using class D, S1 and S2, which helps us to reduce the peak value of the current, and we'll be using the switching circuits. So about the effect of dead time is that if the switch 1 and 2 are on at the same time, it can lead into a short circuit and destroy the device, and also it helps us to perform ZVS. So ZVS occurs in the dead time, so as to, it implies the 0 volt, and we will further analyze it further. And about the ESL value consideration, we have the capacitor, the reactance of capacitive reactance, and the inductive reactance, and so forth. And then when we equate it to each other, we get the frequency of ESLR. So from here, we can calculate the value of ESL. We can use a data sheet to see for what value of frequency is the XC and XLR equal to each other, and from there we can calculate the value of ESL. So the simulation settings, I will be explaining it now, and we have the input voltage of 120 volts. The input resistance is kept to a bare minimum of 1 nano ohm, and the output resistance is 1 ohm. And switching device, I'm using this device. Hemd. The duty cycle is half, the frequency is 27.12, and the parasitic output capacitance is supposedly taken to be 130 picofarad from the data sheet of this device. To calculate the settings for the resonant tank, we have a frequency of given 27.12. From this formula, we can calculate to be 85 and 0.4. For a value of inductor to be 85 nanohenry, we got a value of capacitor to be 0.4. Oh, I'm sorry, I made a mistake. I'm so sorry about it. It's 0.4 picofarad. 0.4 picofarad. But sorry about it. But to make the value, to make the circuit a little bit inductive in nature, so that there is a delayed response on the current and we can achieve ZVS, I will increase the LR to 89. And thus the resonant frequency would be 27.96 in this case. Now, the parameter for the dead time, we can calculate it in such a way that the power loss here doesn't occur. So what is the dead time? It's the time between, it's also a time when both the circuits are off, and during this time, the parasitic capacitance of the switching device discharges. And if the switching device doesn't discharge, which means the dead time is not enough, we will see a power surge here. The current will rise as when the switch turns on, this charge will get delivered here, and then we will see a current peak and a resulting power loss. So we can make the dead time such a value that there is no peak here, and CUSS gets completely discharged. Now for the ESL values from the data sheet, I calculate the value of an MLCC capacitor to be 1.6 nanohenry, and a full capacitor I'm taking the value to be approximately 10 nanohenry for a 0.4 nanofarad capacitance. The simulation for an ideal resonant tank capacitor, we have the gate signal 1 and 2, and when 2 is off, we have the gate, we have the switching device voltage, and this is the current in red. So as you can see, we apply ZVS operation is achieved here. Also to notice is the value is negative here for when the voltage becomes 0 is because the magnetizing current in the resonant group flows during this dead time, and it's always in the opposite direction until the polarity changes. So we get a negative value, and then we have 0 volt switching, and the frequency was measured to be 27.12 megahertz, and the current is 64.66 ampere. For an MLCC, we get similar for a similar situation here, but we introduce ESL, equivalency is inductance of 1.6 nanohenry. And in this case, although we get the output frequency of the current in the inductor, as mentioned here, to 27.12, the current gets reduced, which is because the impedance increases because of the ESL. Although another thing to notice here is that because the circuit is a little bit inductive in nature now because of the 1.6 nanohenry. In the next simulation result, we can see that the same circuit, we can reduce the dead time further from 1.5 to 0.9 nanoseconds, and we still get the same result, let's say of 27.12. Although the current increases, the amplitude of the current increases to 58.25. So as you can, yeah. But in the case of non-ideal film capacitor with a really high value of 10 nanohenry, another thing to notice is that the inductor in our resonant tank has a value of 90 nanohenry. So if we add another 10, that's almost increase of 11% inductiveness of the circuit. And in this case, the dead time was calculated to be 1.1 nanoseconds. Although it brings a huge phase difference, and the current rises after a long time because of phase difference in the circuit. And also the impedance increases significantly, and then the peak value is almost half here. And then the inductive current graph, we can calculate the frequency still equals to 27.12 megahertz. So in discussion, I will just summarize the results a little bit. For the ideal, we get the ESL0, we get the current value. You will see the current value decreases because of the ESL value here. The impedance increases. Although we can decrease the dead time lesser, I think it's because the inductive nature of the circuit helps the parasitic capacitance of the switching device to discharge faster. So we can increase at that time. And the current peak increases. For the non-ideal, the current peak becomes half because of a high impedance value. Now for the ZBS operation. So when the dead time is introduced, when the switch 1 is turned off and the switch is turning on, like I explained before, the parasitic capacitance of switching device 2 starts to discharge. While this starts charging. So unless it's complete discharge, we should not turn it on. We get the peak value. And for a reliable dead time, and to optimize it with the inductiveness of this resonant tank, we should calculate the optimized dead time, and then we can get a higher amplitude of current across this resonant tank. For the conclusion, we determine the significance of dead time for discharging of the parasitic capacitance, and second of ESL of the resonant tank on the source switching operation in the applied simulation. And the result shows that with a high ESL, such as in a film capacitor or an electrolytic capacitor, the net impedance increases a lot and causes the amplitude to decrease significantly. So for a wireless power cross system, the circuit efficiency will be greatly reduced to a lower generation of flux and lower EM electromagnetic induction according to Faraday's law of electromagnetism. Although the power transfer will be more dependent on the quality factor of the resonant tank, and I am thinking of this as a future research in future, although not sure about it yet. And for low value of ESL, it helps lower the dead time and thus reducing switcher loss further. As we have shown in the MLCC, we can use from 1.1 to 0.9. And for future research, I would advise to use direct material having a lower ESL, such as in an MLCC. And also for the further research, it would be appropriate to use consider other factors like ESR, the equivalent series resistance, parasitic resistance of the capacitor, and also the magnetic loss of the inductor should also be considered for application in WPT. So that's all for today. Thank you for the opportunity, and please feel free to ask any questions.